chapter 5, 5.1, sequences. So we're going to talk about sequences, and eventually we're going to talk about series. Then we're going to learn how to use mathematical induction to prove some nice statements. First of all, a sequence is a function whose domain is either all integers between two given integers or all integers greater than or equal to a given integer. So you can consider a sequence as a function that maps, for example, n natural numbers to r real numbers. It takes on natural numbers like n and it maps them into f of n. This is just a function. So we usually write the terms of a sequence using index terms. A sub m, a sub m plus 1, a sub m plus 2, and the last term, a sub n. Each one of these is called a term of a sequence. The very first term is called initial term, and the very last term is called the final term. We usually assign a general term to a sequence. We usually write it f of n equals to a sub n, and we denote the sequence function as a sub n. We're interested in adding the terms of a sequence and form something new. We call it a series. The summation of the terms of a sequence is called series. For example, the sum of a sub k, k starts from m and stops at n, is just substituting m, m plus 1, m plus 2, and so on into k. So the first term, a sub m, because of the summation notation, plus a sub m plus 1, a sub m plus 2, and so on. Since this series has upper limit n, your last term is a sub n. We call k the index of the summation, m the lower limit, and n the upper limit. You've seen series before. We can just evaluate series or just summations by plugging values. Suppose a sub 1, the first term of a series is given, is negative 2. The second term, negative 1, the third term, 0, and the fourth term, 1, and the fifth term is 2. Then the question says calculate each of these summations. The first one says find the sum when k starts from 1 and stops at 5. So you substitute 1, then you substitute 2, substitute 3, substitute 4, and since the upper limit is 5, you stop at a sub 5. The question tells us a1 is negative 2, so negative 2. a2, negative 1, a3, 0, a4, 1, and the last term is 2. Add them all together, the outcome is equal to 0. The second one says upper limit and lower limit are all the same. It means that we only have one term. If you plug in 2 for k, get a sub 2. A sub 2 is negative 1, so the outcome is minus 1. See, Now you're changing the index. You're saying that instead of having just k, I want to multiply k by 2. Then we start substituting k values. If k is 1, a sub 2k is going to be a2. If k is 2, a sub 2k is a sub 2 times 2. So you have a sub 2 plus a sub 4. A sub 2 is -1 plus a sub 4 is 1. The outcome is equal to 0. Let us move on to the next page. Mathematical induction. So suppose you have some statements that they built on using some terms of a sequence or a series based on a sequence. How do we prove that? In general, assume that P of n is a property or a statement. Suppose A is a fixed integer, the very first value in the domain. So first value in the domain, in the given domain. Suppose the following two statements are also true. If you plug in A for n, that statement is true. Inductive step. 2. For all integers k greater than equals to a, if pk is true, then you can conclude that pk plus 1 is also true. Mathematical induction says, if you have these two conditions, then the statement itself is true for all integers greater than equals to a. This method of proof is called mathematical induction. So, method of proof by mathematical induction. First, you have to identify your property or the statement. Step 1, which is the base step, you plug in the very first value in the domain and you need to show that that statement is true. Second step, which we call inductive step, is saying that suppose pk and then pk plus 1 are true statements. Finally, eventually, you conclude that Pn as the general statement is a true statement. Let's go over one example to feel more comfortable about this method. Theorem: for any integer greater than equals to 1, the sum of the first n numbers follow the formula n times n plus 1 divided by 2. So you have left-hand side and you have right-hand side. Your goal is to show that this statement is true by using mathematical induction. So first of all, let us identify Pn. This statement, left-hand side is equal to right-hand side, is your Pn. The first element, the first number in your domain is 1. So we plug in 1 into the statement that we have and we show that it is true. If you plug in 1 on the left-hand side, the very first term is 1 itself. So we don't have anything else for left-hand side. But for the right-hand side, if you plug in 1, you get 1 times 1 plus 1 divided by 2. You can cancel out 2 and 2, which is 1. Left-hand side is equal to the right-hand side. So you just prove P of 1 is true. Now let us move on to inductive step. We assume pk is true, then we show that pk plus 1 is also true. So since pk is true, it means that 1 plus 2 plus 3 up to k is equal to k times k plus 1 divided by 2. So we know that left-hand side, right-hand side are equal to each other for k. Our goal is to show that pk plus 1 is true. What's the meaning of that? It means that if I plug in k plus 1 on the left and right-hand side, I must get an equality here. Note that on the left-hand side, you have 1 plus 2 plus 3 plus k plus 1. Don't forget this term k in the middle. 1 plus 2 plus 3 plus k plus 1. Okay, get back to pk. pk says if I add the first k natural numbers, it is equal to k plus 1 divided by 2. So let us substitute k plus 1 divided by 2 for 1 plus 2 plus 3 plus k. And you have the last term, which is k plus 1. Take common denominator between these two and add the numerators. K times k squared plus k divided by 2 plus 2k plus 2, which is equal to k squared plus k plus 2k, 3k plus 1 divided by 2. Very well. Okay. So their product is equal to 2, and their sum must be equals to 3. So if you write it in factored form, their product, so this is 2, not 1. So let me fix that. So the factored form is equal to k plus 1 times k plus 2 divided by 2, which, as you can see, is equal to the right-hand side. So you started from left-hand side and show that left-hand side is equal to the right-hand side. So we just prove pk plus 1 is true. So what's the meaning of that? It means that the general statement Pn is always true. Another example. Apply the formula for the sum of the first n integers. Very well. So the first part says, what's the sum of 2, 4, 5 up to 500? Okay. All of these numbers have factor 2. So let us factor out 2, and then we have 1 plus 2 plus 3 up to 250. So our n is equal to 250. We can apply the formula that we learned here in previous theorem. The sum of 1 plus 2 up to n is equal to n plus 1 divided by 2. And here our n is equal to 250. So you have 2, you copy down your 2, 250, 250 plus 1 divided by 2. So you can cancel out 2 and 2. The sum is equal to 62. 750. Let us take a look at B. It says evaluate 5 plus 6 plus 7 plus 8 up to 50. As you can see, some initial numbers are missing. So we cannot apply the formula now. We need to have 1 plus 2 plus 3 plus 4, which are missing from the sum. So what we can do, we can add and subtract those numbers. We can add 1, 2, 3, 4, and at the same time subtract the sum. Then apply the formula to the sum 1 plus 2 plus 3 up to 50, which we know already it is 50 times 50 plus 1 divided by 2 minus this sum, which is 10. After doing a little bit of algebra, the sum is 1,265. Finally, part C. The sum starts at 1, then 2, then 3. The last term, we don't have any number for that. It means that our n is equal to h minus 1. So by following the formula, we have n, which is h minus 1, times n plus 1, which is h minus 1, plus 1. You can cancel h and h. The outcome is h minus 1 times h divided by 2. This is your sum. Very well. You saw geometric series in calculus. So here's the formula for you, and we're going to use mathematical induction to prove this formula. For any real number r, except 1, and any integer n greater than or equal to 0, the sum r to 0, r to 1, r squared, r cubed, dot, 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 r to the n is equal to r n plus 1 minus 1 divided by r minus 1, which is geometric series that you saw before. We can prove this formula by using mathematical induction. First of all, the very first value in our domain is equal to 0. So we have to check to see if P of 0 is true. Wherever you see n, you write 0. Your n is equal to 0. It's not r. So the sum I from 0 to 0, r to the I, is this guy equals to r to 0 plus 1 minus 1 divided by r minus 1? This is your goal. You need to show that left-hand side is equal to the right-hand side. On the left-hand side, the term starts and stops at 0. Okay, if I plug in 0 for I, any non-zero number raised to 0 is 1. On the left-hand side, you have 1. What about right-hand side? On the right-hand side, you have r minus 1 divided by r minus 1, which is equal to 1. Left-hand side is equal to the right-hand side. So we're good with P of 0. Next step is to show that it is true for pk, then you prove it for pk plus 1. Perfect. So suppose P of k is true. It means that if I plug in k for n, the sum I starts from 0 to k of ri is equal to r to k plus 1 minus 1 divided by r minus 1. So I already know that this statement is true. My goal is to show that pk plus 1 is true as well. Very well. When I plug in k plus 1 for n, I can write the series in expanded form. The sum I starts from 0 to k plus 1 is the sum I starts from 0 to k and plus the last term, which is r to k plus 1. I just plug in the upper limit into the term and I copy it down next to the series. Now let us use pk, which we already know is true. The sum I starts from 0 to k is nothing but this rational expression, r to k plus 1 minus 1 divided by r minus 1. We just substitute this rational expression for the series and we copy down the last term here. Now we take common denominator, which is r minus 1, and we try to simplify as much as we can. Rk plus 1 minus 1 plus, we distribute Rk plus 1 into parentheses, which gives us Rk plus 1 minus 1 plus Rk plus 2 minus Rk plus 1. So these two are opposite terms. The outcome is R to k plus 2 minus 1 divided by r minus 1. This is the rational expression that we tried to prove. So, because of mathematical induction, we say that the statement itself is true. We just proved the sum of geometric sequence. Another example for you. For all integers n greater than equals to 0, 3 is a factor of 2 to 2n minus 1. To prove these statements, we can use mathematical induction. Perfect. First of all, let us identify Pn. Pn is the statement saying that 3 divides 2 to the n minus 1, or 2 to the n minus 1 is divisible by 3. The very first element in your domain is 0, so your goal is to show that P of 0 is true. It means that wherever you see n, you plug in 0. Very well. 2 to 2 times 0 minus 1 is 1 minus 1, which is equal to 0, and you know that 3 divides 0. Of course, 0 can be written as 3 times 0. So this is always true. Next, suppose pk is true. Your goal is to show that pk plus 1 is also true. So we say that suppose 3 divides 2 to 2k minus 1. Suppose this statement is true. Our goal is to show that 3 divides 2 to 2k plus 1 minus 1. This is our goal. Perfect. So we're going to use what we have and prove this statement. Here you can do factorization. What do I mean by that? You have a statement that you need to show that 3 is hidden here somewhere. 3 is a factor of this statement. So let us take this statement and try to write it in factored form. First, distribute 2 into the exponents. 2 to 2k plus 1 minus 1 is 2 to 2k plus 2 minus 1. What do you have here? You have 2 to a plus b, the sum of exponents that you can write in separate form. You have 2 to 2k times 2 squared minus 1. Note that 2 squared is 4 and 4 is attached to 2 to 2k. It is not 4 minus 1. It is not 3. Then you can write 4 as 3 plus 1. Then distribute 2 to 2k into parentheses, which is 2 to 2k times 3 plus 2 to 2k, and you copy down minus 1. Very well. Let us get back to the statement that we have. We know that 3 is a factor of 2 to 2k minus 1. So this statement here has 3 in it. 3 divides 2 to 2k minus 1. We're almost done. Why is that? Because we have 3 as a factor of this statement, this term on the other side. 3 divides this term. 3 divides this term, so 3 divides the sum. It means that we just proved 3 as a factor of this statement. So by getting back to mathematical induction, this statement in general is true. Another proposition. This proposition says for all integers n greater than or equals to 3, 2n plus 1 is less than 2 raised to n. Let us use mathematical induction and start proving this statement. Let us identify Pn, which says 2n plus 1 is less than 2 to n. Then, since the smallest value in our domain is 3, we have to calculate P3. So, we have to show that when n is 3, this statement is true. That's obvious. If you plug in 3 for n, you get 2 times 3 plus 1, which is 7. If you plug in 3 here, you get 8, which says 7 is less than 8, and it is always true. So we're good with the base step. Now, let us move on to inductive step. Inductive step says, suppose pk is true, show that pk plus 1 is true. So suppose 2k plus 1 less than 2k is always true. Now our goal is to show that if I use k plus 1, this inequality is still true. Very well. Okay. 2k plus 1 must be less than 2 to k plus 1. But how do we prove that? First of all, here we have a question mark. We need to prove left-hand side is less than right-hand side. So let us start by writing left-hand side and start seeing what's going on. 2k plus 3 can be written as 2k plus 1 plus 2. At the same time, using pk, you know that 2k plus 1 is less than 2k. Also, 2 is always less than 2 to k when k is greater than equals to 3. If you add these together, you have 2 raised to k plus 1, which is 2 times 2 to k. So we started from left-hand side, 2k plus 3, and we showed that the left-hand side is less than right-hand side. By induction, we prove that this inequality is always true for n greater than equals to 3.